Thank you everybody for coming. I'm very happy for the colloquium talk today with Mateusz Kwaśnicki. I'm going to read a short paragraph that I found at the Polish Academy at the webpage. So Mateusz Kwaśnicki is a mathematician at the Faculty of Mathematics at Wroclaw University, Science and Technology, winner of the EMS Gordon Prize, Kazimierz Kuratowski Award, and the Polish Mathematical Society Prize for Young Mathematicians, as well as Foundation for Polish Science and Ministry of Sciences and Higher Education Scholarship. He wrote his master and PhD thesis under the supervision of Professor Tadeusz Kuczynski, member of the research group funded by Tomasz Biurkowski. Although he's a theoretical mathematician, he published at the Journal of Engineering Mathematics. In his research, he studied relations between a stochastic process, differential equations, and pseudo-differential operators. He proved equality of operator node of the discrete and continuous Hilbert transform on LP, thus solving a 90-year-old problem posed by Rees and Teichmark. And if I understand there is an anecdote, no? It was posed to you by Rodrigo Bañuelos, no?
Yeah.
A few years ago in Poland, no? And he didn't tell you it was a very hard problem. And
yeah, that's the story. Joined the chat between Rodrigo and Eros Saxman. And they said, oh, you should work on that problem. And I said, okay, it's fun. But I forgot to mention that it's kind of hard.
And well, being a little bit more informative, your talk today is going to be also like a very well-known problem in several areas, no? In PDEs, in probability and in operator theory, and it's actually I consider one of the difficult problems. No, you have solved a one-dimensional. What you're going to present now today is a one-dimensional characterization of these operators, and was also posed in one of the last sections in this famous paper of Caffarelli and Silvestre. No? So I think that sense is a very beautiful topic, no? That will integrate together many areas here at CIMAT, and I think a lot of people will appreciate. So thank you very much, Mateusz. It's my pleasure to introduce your talk.
Thank you very much. I'll just start sharing my screen. Okay, should see my screen now. Thanks for this introduction. Well, I started to feel pressure after that. Yeah, so I was indeed give a talk which is somewhere on the boundary between probability theory and PDEs. So it has essentially two titles. For those of you who prefer Pde language, it's extension technique for non-symmetric operators. And for people working in probability, it's boundary traces of non-symmetric diffusions, which turns out to be the same subject in the end. But the relation is quite intuitive, but not clear at the technical level. It's actually turned out to be not clear at all. So I'll start with something very, very basic and very, very classical. So the usual Dirichlet-Neumann operator in one of the simplest possible domains in the Hall space. So what we are going to do is to consider the Laplace equation. So the delta U, the Laplace operator applied to U is equal to 0 in a half plane, so in two-dimensional space with a prescribed boundary condition. So on the boundary, we require U to be equal F. F is some boundary data, just to fix our attention, to restrict our attention to something which is more or less intuitive. Let's think it's a square integrable and continuous. But in fact, you can work with marginal ones. But in this talk, let's consider L2 and to have everything pointwise, just think it's continuous as well. Okay, so we have this Dirichlet problem, and we know that if we assume some boundedness of U, for example, then the solution is unique. And the solution is in fact given by the Poisson integral. So you need to take your boundary data integrated with respect to what is called the Poisson kernel, which is given by an explicit formula in half. Well, this is for the half space. We'll only consider two-dimensional things in this talk, but some formula are written in more general context. So D is the dimension here. In the Poisson kernel, dimension 1 is just y over y squared plus z squared. And you need to convolve this with your boundary data. And that gives you a harmonic function with prescribed boundary data. And that's a very old result going back to 19th century, to early 19th century. And it's essentially due to Poisson, but many more people contributed to that. And in 1940s, Kakutani was probably the first one to observe that this is closely related to the Brownian motion. And you can characterize a solution of this Dirichlet problem in a probabilistic language by starting a two-dimensional Brownian motion at the point x, y in the plane, so here, at that point, and waiting until it exits the half plane at some point. Well, say this happens at time tau. So this is a point of coordinates x tau, 0. Okay. Well, call it tau h. We'll not use other exit times here, but let's call it tau h. So this is the first exit time from the half plane. And if you average your function f with respect to the distribution of that random exit point, you will recover the harmonic function u. Okay. So in this case, u is called the harmonic extension of the function f. And the Dirichlet to Neumann operator is defined to be simply the normal derivative at the boundary. Well, the normal derivative here means just the derivative with respect to the y variable. And the Dirichlet to Neumann operator maps the boundary data, which is f, to that normal derivative. And in this simple case, you can calculate this explicitly because, well, the normal derivative is just that limit. And if you plug the formula for u into that limit and ignore technicalities, well, what you get is, well, y cancels out. And in the end, you get the kernel 1 over z squared in dimension 2, or in general, 1 over z to the power d plus 1 times f of x plus z minus f of x. Okay, this is not really integrable, so you need to either regularize this or consider this integral as a Cauchy principal value integral. And that's one of the famous operators. That's the square root of the Laplace operator with a minus sign inside. And you can see that by considering Fourier transform, for example. So if you move to the Fourier space, so take the Fourier transform of the function u with respect to the variable x. So you leave y as it was, you just Fourier transform x. Then the Fourier transform of the Poisson kernel is just the exponential of minus y times mod xi, where xi is the Fourier variable. And the convolution, of course, is mapped into the product of these two functions. Okay. And now we can take the derivative, and again, ignoring convergence issues and things like that. Well, the derivative of the exponential is just the coefficient in the exponential, in the exponent. So this Dirichlet to Neumann operator k turns out to be the Fourier multiplier with symbol minus mod xi. And the Laplace operator is a Fourier multiplier with symbol mod xi square with minus sign. So at least formally, you can say that you need to put a minus sign in front of the Laplace operator, take the square root of that, and then add another minus sign. Okay, so that's one way to understand why we call this operator the square root of the Laplace operator. There are many more, of course. And that's sort of well understood. But let me go back to this probabilistic interpretation. So once again, we consider a two-dimensional Brownian motion started at a certain point x, y. And instead of killing it or stopping it at the time when it hits the boundary, let's reflect it at the boundary. There are many ways to construct that, but the simplest one here is just to kind of to fold your sheet of paper into two and see what is the process. So it kind of moves from back to front and vice versa. Okay, so we consider a reflected Brownian motion in the half space, and now we would like to understand what is the probabilistic meaning of that operator K. In order to do that, in fact, we should look at the trace that the two-dimensional Brownian motion leaves on the boundary. On the boundary means on the horizontal axis. But it's not really straightforward how to define the trace. The right way to do that is the use of so-called local time. So it kind of, what we want to do is to erase the part of the trajectory that is above the line y equal to epsilon, so that line. So we just kind of ignore everything that happens up there and just look at the path in this narrow strip. And then we make this strip thinner and thinner and see what the limit is. The problem is, if we go with epsilon to 0, then the process spends less and less time in that strip. So we need to normalize that time appropriately. And the way to do that is as follows. So you measure how much time did your process spend in the strip up to time t. So we take the indicator of ys, the indicator of 0 epsilon of ys, and integrate it from 0 to t. We choose the normalizing factor, which is 1 over epsilon, and then pass with epsilon to 0. It turns out that this has a non-trivial limit. It's a continuous process, which is increasing. It's non-decreasing, and it increases only when the two-dimensional process is on the boundary. So only when yt is equal to 0. Okay, and our clock, our local clock, is given by the inverse local time. So we take the inverse of that function. It's not strictly increasing, so we need to think of the right or left inverse. And the right way to do this is written here, but essentially this is just the inverse function. This one was piecewise constant, so this one will have a lot of jumps, because constant parts on the graph of LT will be mapped into jumps of capital TS. And by observing that everything is scale invariant here, so if you just zoom in or zoom out, you get the same picture, just the time is different. It runs, an appropriate number of times faster or slower. You can easily see that what you get is a Levy process, an increasing Levy process, hence a subordinator, which is scale invariant, and hence it's necessarily stable, with index of stability easily calculated to be 1/2. So this is called 1/2 stable subordinator, and this gives us the times. Ts is an instant of time at which the two-dimensional diffusion is on the boundary. And we can look at the trace process. So we just look at, the vertical coordinate is boring because it's 0 at each time when the process is on the boundary. It's 0 by definition. But we look at the process of these red dots. So the x-coordinate measured only on at the times given by the inverse local time. Okay. So this process, ZS, is just a process which is a jump process that, let me move up a little bit, that goes from one red dot to another by jumps of the two-dimensional process. Okay, so it will jump over there, and backwards, again backwards, and so on. So that's pure jump Levy process. And this was observed in 1958 by Spitzer, and proved that this is a Levy process, in fact, one stable Levy process. So it's kind of scale invariant. If you zoom it in k times, then you need to run your clock k times faster or slower to observe the same process. And again, this follows easily by just looking at the picture and thinking about how it scales. And this is also called a Cauchy process, especially in dimension 1, because its one-dimensional distributions are the Cauchy distributions. And if you prefer to speak in terms of the Gaussian coefficient, drift, and the Levy measure, there's no Gaussian coefficient, there's no drift, and the Levy measure is just the power function. So in dimension 2, which I'm interested in most, so you get the one-dimensional boundary trace process, and the Levy measure is just 1 over z squared up to some normalization factor. Okay. So now we have two ways to view the operator k. Either this is the Dirichlet to Neumann operator, or it's the infinitesimal generator of the process Zs, of the process of the trace process. Okay. And this is in fact very classical, both in analysis and probability, and it has been extended to more general Levy processes. The most famous extension is due to Molchanov and Ostrowski in the world of probability, and to Caffarelli and Silvestre in the world of PDEs. Okay, so we keep the horizontal coordinate, we do not change it, it's still just the usual Brownian motion, but we change what happens on the vertical coordinate. So now we want vertical coordinate to be another diffusion. And the right one to still have some scale invariance is the so-called Bessel process. The Bessel process of integral dimension is just the distance to the origin of the d-dimensional Brownian motion. But then if you look at it as a one-dimensional diffusion, you can kind of interpolate between different dimensions and get a Bessel process of dimension arbitrary real. And here we consider the Bessel process of dimension 2 minus alpha, where alpha is any given number between 0 and 2. And it turns out that the boundary trace process, which is defined in a very similar way as before, is again stable, but the index of stability, the index of stability now is equal to alpha. So what we get is an alpha stable Levy process, which is rotationally invariant, or in dimension 1, it's just symmetric. That's called isotropic. And that was proved first by Molchanov and Ostrowski in 1969. And of course, alpha equal to 1 corresponds to the classical case, because the Bessel process of dimension 1 is just the Brownian motion reflected to the boundary. In general, the definitions are really very, very similar. You need a different scaling factor in the definition of the local time. In order to get a non-trivial limit, the right normalization is given by epsilon raised to the power of alpha. And again, by scaling, you can see that the inverse local time is alpha half stable instead of just 1/2 stable. And it's again a stable subordinator. And the subordinate process is just alpha stable. Now, if you prefer to speak the Pde language, you should look at the infinitesimal generator of your two-dimensional diffusion. So the generator of the bivariate process x dy t is just the Laplace operator in both variables plus a drift term. So the most classical second-order elliptic operator, the Laplace operator, perturbed by a first-order term with the coefficient 1 minus alpha over y, which is singular near the boundary. So that's more or less the classical case in PDE theory, except for that the perturbation is not really nice near the boundary. It blows up near the boundary unless alpha is equal to 1, which is the classical case. And then again, you can just sit down and have a look at the Dirichlet to Neumann operator, what it is. There's a minor change in the definition of the Dirichlet to Neumann operator. You again need a different scaling to get a non-trivial limit. So there's a normalization constant, which we don't really care at all about. But instead of just taking the normal derivative at the boundary, you need to take somehow a weighted normal derivative. So you take the normal derivative, the derivative in the normal direction, close to the boundary. You multiply it by y to the power 1 minus alpha, and then pass the limit with y to 0. Now, if alpha is equal to 1, you just recover the usual normal derivative at the boundary. But if alpha is not equal to 1, you get something else. And it's in fact more convenient to use the definition of the derivative and write this in the following form. So you just take a weighted difference quotient of the function u at the boundary. So the u of xy minus u of x0 divided by y to the power alpha. So that exponent alpha is unusual in the denominator. You go to the limit as y goes to 0, multiplied by normalization constant. And what you get is, again, a nice singular integral operator. You get essentially the same expression for the function u as in the classical case. So these two lines are kind of classical, but the next line was a key observation of Caffarelli and Silvestre in their famous 2007 paper, where they observed that u is in fact given by a Poisson type integral, and the Poisson kernel is essentially the same, except that the exponent is different. The Poisson kernel for the classical case had exponent d plus 1 over 2, and here you have d plus alpha over 2. And now you can do the same operations before and pass to the limit as y goes to 0. And in the end, you get the same operator with a different kernel. The kernel is then 1 over mod z to the power dimension, 1 in our case, plus alpha. Okay, and that's a basic formula for the fractional Laplace operator of index alpha half, I mean, of index alpha, but alpha half power of the Laplace operator. And in order to see that, again, you can look at the Fourier transform. I did not write the formula here because they are kind of complicated, but it's in fact fairly standard to calculate the Fourier transform of, say, the function u and see that the Fourier multiplier there satisfies certain differential equations and solve it. It's Bessel, essentially it's a Bessel differential equation. So the solution is given by an appropriate Bessel function. You can pass to the limit again and see that the Dirichlet-Neumann operator k is a Fourier multiplier with symbol minus mod psi to power alpha, which indeed tells you that you get the fractional power of the Laplace operator. This calculation is due to Caffarelli and Silvestre. They did both the spatial variable calculation and the Fourier transform variable calculation. But the calculations in Fourier transform in different contexts are in fact much older. There's a paper by Mackenhaupt and Stein from 1965, and there are at least 2 other papers which have very similar calculations. But as far as I know, all of them worked only in the Fourier variable, and none of them worked in the spatial variable. So that's the true contribution, and that kind of explains how why this paper by Caffarelli and Silvestre was so influential on the development of this theory. Okay. Now we can try to extend it in various directions. The first obvious extension is to consider similarly defined fractional powers of other elliptic operators. You can substitute essentially whatever you like for the Laplace operator and check whether this procedure works as expected. Turns out that it usually does, and there are many papers. In fact, I should write plus many more here. This is just a sample of papers where extensions of that form have been studied. And in most cases, L0 was a nice symmetric elliptic operator, but in fact, there are also some of these papers deal also with more general generators of strongly continuous semigroups on Banach spaces or things like that. And you can see that these papers are span for the entire past decade, and it's still an active field of research. The result that was mentioned by Héctor in the introduction is in fact from my paper with my PhD student Jacek Mucha, and it indeed answers a question raised in the paper by Caffarelli and Silvestre, which asked for what class of operators can be obtained by considering similar extensions, where essentially you have the Brownian motion or the Laplace operator on the x-coordinate and whatever you like continuous process on the y-coordinate. And this turns out that you always get a subordinate Brownian motion, or in Pde language, you get a function of the Laplace operator for a psi of minus delta for a nice psi. In probabilistic language, you can't get really any subordinate Brownian motion, but there's a way to describe all possible processes that you can get. And these are precisely subordinate Brownian motions which correspond to so-called complete subordinators. And in the Pde language or language of analysis, what you get is a complete Bernstein function psi of the Laplace operator with a minus. So I will not dig into that now. So in particular, I will not explain what a complete Bernstein function is. But there's a one-to-one description of these operators. And Hector said that's a nice result. Indeed, I like it very much, but in fact, it's not ours in a sense. We just translated what was known in the field of one-dimensional diffusions and their local times and their inverse local times and the corresponding analytical results into the language of harmonic extensions. So the credit should go to Krein and his collaborators and descendants, because this was all based on the so-called Krein spectral theory of strings. And I will mention, I will discuss a closely related subject, but I will not really dig into that paper again. And this was further extended in at least two papers by Assing and Hermann in, well, the preprint appeared in 2019, and more recently by Hauer and Lee, where they consider more general elliptic operators, L0, and essentially arbitrary complete Bernstein function psi. And in Assing and Hermann's paper, L0 is a generator of nice diffusion on RD. And in the paper of Hauer and Lee, this in fact need not be even a linear operator. So this is a really, really general result, which I must admit I do not really understand well enough to appreciate it fully. But what I was interested in is sort of a different line of research, which also aims to extend these kind of results, but in somewhat different direction. Because it turns out that if you consider non-symmetric stable processes, or in the Pde language, non-symmetric fractional derivatives, then essentially there is no similar description of these operators. Of course, if you just take one-sided derivative or subordinator, or stable subordinator, then this becomes, in fact, the degenerate problem in some sense. And of course, there are many descriptions of these kind of both processes and operators. But what I was interested in is the general case. So the question that I tried to answer was, can we do the same for arbitrary, not necessarily symmetric, stable process? And it's fairly easy to see that this won't work in higher dimensions. So we can't get just any stable process by just varying a finite number of coefficients, because just the dimensions do not agree. There are just too many stable processes in a sense to get all stable processes in higher dimensions. But there seems to be no obvious obstacle in dimension one. So the question that I was focused was, can we write a similar expression for one-dimensional non-symmetric stable processes? Can we somehow describe them as boundary traces of certain diffusions? And this is not really a difficult problem, but it led me to a more general question of what kind of operators can be obtained, or what kind of processes can be obtained by observing the trace of two-dimensional diffusions on the boundary, or by considering the Dirichlet-Neumann operators of elliptic differential operators in a half plane. And let me start with the probabilistic formulation, because that's the language that I prefer. And only at the end, I will move to the Pde formulation. And we need a few definitions. So we need to know what we are working with. So we'll consider a continuous strong Markov process, xt, yt, with values in R. So xt is a real valued process, yt is a non-negative valued process. In fact, we allow for slightly larger generality. So yt can live in a finite interval from 0 to capital R. But for the purposes of this talk, let me just ignore this. I will just show one picture which tells you what happens there. And in the slides, some details are given, but I'll just ignore that case. Okay. And we call this process a shift invariant diffusion if, well, first of all, it is a diffusion. So it's a continuous process. And it is shift invariant, which means that if you translate it to the left or to the right, so that the boundary of the half plane is preserved, you get the same process started at a different point. So formally, if you consider a shifted process, so you use p plus xt instead of xt for whatever real p, then you get the same process, just started at a different point. But its law is the same. Okay? And that's one more technical condition. We want this process to be reflected at 0. And in case when its lifetime is finite, then we want the y coordinate to go to infinity. The y coordinate can have a huge drift towards infinity, for example. It's just a diffusion process. And then we need to require that it really goes to infinity and not stop somewhere inside. Okay, so that is kind of non-triviality or non-degeneracy assumption. In fact, we do not really need full reflection. It can be a stick reflection at 0. So we work essentially in most general possible context here. And it turns out that by appropriate manipulations on that process, you can transform it. And I will describe how to transform it when I will move to the Pde language into something that I call a regular shift invariant diffusion. So in the regular shift invariant diffusion, we have a number of restrictions. So first of all, yt is not just any diffusion, it's just the Brownian motion. So the vertical coordinate is the Brownian motion. Note that this is not in agreement with the usual description of the Caffarelli-Silvestri extension, where yt was a Bessel process, so it was not Brownian motion. But you can kind of transform Bessel process into the Brownian motion by appropriate manipulations. And we also require that xt essentially has no drift. So formally, it's a local martingale. Okay, so that seems to be much more restrictive, but it turns out that every shift invariant diffusion can be turned into a regular shift invariant diffusion. And I will come back to that later. So instead of all these definitions, perhaps it's better to show you some pictures. So here's a picture to keep in mind. And in a minute, you will see real life simulations, so to say. So we consider a two-dimensional process which essentially behaves in the same way on each horizontal line. Okay, so if you just move it a little bit left or right, it doesn't change its behavior, but it can change its behavior when according to the distance to the boundary, essentially. So for example, here near the boundary, the y coordinate has much faster evolution than the x coordinate. Away from the boundary, the evolution is more or less the same, but you get a lot of drift toward the right. And then above some level, it's just a Brownian motion, essentially. That's what I tried to show in the picture. Okay. In the more general case, you're also allowed to put an absorbing barrier at some point. Okay, so here you have absorbing barrier at the top and reflection at the bottom. Okay. And these are more or less Ito diffusions. So you need some regularity on the coefficients in order to write this as an Ito diffusion, but philosophically, these are just Ito diffusions. And Ito differentials of these processes can be written in terms of two independent Brownian motions using some square matrix sigma plus some drift term. And in the regular case, when the diffusion is just a Brownian motion in the y coordinate, and the x coordinate is local martingale, you no longer have the drift term because you have local martingale, so the drift term is gone. And also one of the well, the second row of sigma is just 0, 1. Okay, so yt is just a Brownian motion, and xt is a y-dependent local martingale. So here the coefficients do not depend on x; they just depend on y. Okay, so we have essentially 2 degrees of freedom at each level: sigma 1, 1 and sigma 1, 2. Okay. Now, if you want to write the Pde counterpart, you need to know what is the generator of that diffusion, because the trace will correspond again to the Dirichlet-Neumann operator, and in order to define the Dirichlet-Neumann operator, you need to know what kind of harmonic extension you consider. So that if somebody is ignoring probability, then wake up now. Now I'll speak a little bit of Pde language. So what do we have here? We have a second-order elliptic operator. In the general case, we just have a general second-order elliptic operator, but with coefficients which only depend on y. That's the shift invariance condition. And in the regular case, the drift term, the linear term, is gone, and the coefficient at the second-order derivative with respect to y, the c of y here, is equal to 1. So we want to have the Brownian motion in the y-coordinate. Okay. And now you can. Okay, that I'll discuss in a minute. We need one more definition. So the boundary trace will turn out to be a very nice Levy process. It's clear that it will be translation invariant, so it will be indeed a Levy process, but not just any Levy process. It turns out that it will have a Levy measure, so the measure describing the jumps of this process, with a density function that I call mu of z. And mu of z is not just any function. It turns out that it's a completely monotone function on 0, infinity, and a mirror image of that, well, possibly a different completely monotone function on the negative half line. So mu of z and mu of minus z are completely monotone functions. Okay. A completely monotone means either that the derivatives have alternating signs, or perhaps better, they are Laplace transforms of positive measures. So these are very nice functions which are monotone decreasing, well, positive, monotone decreasing, concave, the third derivative is again negative, and so on. So we have a lot of regularity here. And the theorem tells you the following. So first of all, if you take a shift invariant diffusion and consider the trace process, which is defined again using the local time at 0, which is defined in the usual way, very similar to that I described above, then you get a Levy process with completely monotone jumps. And not just that, you can get any completely monotone, any Levy process with completely monotone jumps in this way. And if you restrict your attention to just regular diffusions, then you get a one-to-one correspondence. Okay, so that's full identification of boundary traces in a regular case with the coefficients of the diffusion, and any other diffusion can be mapped into a regular diffusion in an appropriate way. And I already told you that the result with Jacek Mucha was based on Prime's spectral theory of strings. Here, the situation is similar. All the really hard and nasty job was done by someone else. And this time, this was Eckert and Kostienko, who published a paper in Invenciones in 2016, where they extend Prime's spectral theory of strings, so the theory of certain second-order ODEs, to the context that's a little bit oversimplifying, but it fits perfectly into what was needed here. Okay, so once that is done, the philosophy is clear. The details are totally nasty, but well, it works. You need to, in fact, use all the nice machinery of probability theory. So first of all, you need to observe that your two-dimensional diffusion process is a Markov additive process, and use certain pieces of the theory of Markov additive processes, which I was very surprised actually to see that it applies in this context. And there are a lot of additive functionals of Brownian motions involved, and you already seen that local times are important, and you need to know how to handle them in this more or less general setting. And only in the end, you need to translate the problem into the language of analysis that fits the paper of Eckert and Kostienko. And in order to do that, you use certain characteristic functions and apply Ito's lemma to after taking some expectations. So the technical details are really nasty here. The machinery is very nice, and you really need to use at certain points the most general available versions of that. That was really fun. I really liked how it all worked in the end. And you can, depending on what's your favorite piece of probability theory, you can reformulate the result in different languages, different probabilistic sub-languages, so to say. So you can, for example, say that this tells you something about excursions of these 2D diffusions from the boundary. Okay, so you start your diffusion at the boundary point, and essentially you condition it not to hit the boundary immediately and see where it hits afterwards. And the theorem tells you that the distribution of that jump is precisely the kernel of your operator, which means that it has a density function, which is completely monotone here, and completely a mirror image of completely monotone function here, and another completely monotone function there. And vice versa, for any such two completely monotone functions, you can cook up shift invariant diffusion that gives you the prescribed distribution of jumps. You can also write everything in terms of functionals of Brownian motions, but I'll just skip that part. Now, I promised you some examples. So let me describe what you will see. You can, in fact, given any two coefficients, you can construct a regular shift invariant diffusion as follows. You take two independent Brownian motions. One of them will just give you the y coordinate, so that's bt2 in this picture, and it will also contribute in some way to on the x coordinate, and the other one will just correspond to the motion, additional motion of the x coordinate, and the coefficients of these two are given by two functions. One of them is called b, and the other one is called sigma. Okay, and now b is just the same coefficient that was mentioned above. It's in the Pde language, that's coefficient at the mixed partial derivative. And sigma is the corresponding missing part of a. So we can decompose a to sigma square plus b square. Okay. And it's better to think about images. So you can think that you have two Brownian motions. One of them tries to move your process along horizontal lines, and the speed of that depends on the distance to boundary. And the other one follows what I call profile lines, these blue lines, which are given by integrals of b of y. B is the coefficient. And since you have a local martingale and these lines are curved, it's not really a Brownian motion along these lines, because that would not be a local martingale. You get something that I called apparent drift. So it will move from one line to another, and these are marked by red arrows in this picture. And these red arrows are just to tell you what the second derivative of that profile line is. So they are given by b prime of y. Okay, and now here are some examples. So that's kind of an artificial example. So you put sigma to 0, so there's no motion along green lines, and b equal to, say, sine of y. So you get essentially a one-dimensional diffusion in half plane, which it has no horizontal component, but due to apparent drift, it moves from one profile line to another. And if you look at the trace, it's a kind of jumping process, which is really difficult to describe in that case because you have no explicit expressions for solutions of certain differential equations. So that's really an artificial example just to show you how it works. If you want something more practical, you can, in fact, use similar construction for subordinators. So if you keep sigma equal to 0, and you set b to be appropriate power of y, then you can get essentially any alpha stable subordinate, not really any alpha stable subordinator. Okay, so you have a Brownian motion going along these profile lines, which moves from one profile line to another due to apparent drift, and it turns out that the trace process is just a subordinator. This corresponds to alpha equal to 0.4. Here is a picture corresponding to alpha equal to 0.8. So you see that the jumps are much more dense here. And you can do the same for alpha greater than 1. And it's no surprise that you will get a stable process with one-sided jumps. So in this case, with no positive jumps if B is positive. So here the situation is a little bit more complicated because the motion of that process on the boundary is a little bit more complicated. You need it kind of automatically gets a huge drift in one direction. So it has only negative jumps, but it has a huge positive drift on the boundary, which is not artificial. It kind of comes from the definition of that process. So here's a picture for alpha equal to 1.2. Here's another picture of 1.6. But let me move on. If we add the green part, it's not green in the picture, sorry. The pictures are just taken from the article. But here we add this green horizontal motion, which is bigger and bigger the further we get away from the boundary. And if we, again, use appropriate powers of y for both sigma and b, what we get is a general alpha stable process. So here alpha is equal to 0.5. And you can see that there is one huge jump that will probably lead us somewhere far, far to the right of that picture. Here's a picture for alpha equal to 1.5. So you see that there's picture is much more complicated and a lot of small jumps here, just as expected. And let me mention one more example. This is really general, so we can consider essentially any drift coefficient and any two coefficients b and sigma for which the problem makes sense. In particular, sigma can be a measure. So you can consider a process which just moves as a Brownian motion up and down until it reaches a certain level at which it gets kicked by an independent Brownian motion. So whenever it reaches that level, it moves a little bit to the left or to the right. That corresponds to atoms in the measure sigma. And you can also consider b piecewise constant. And at the places where b jumps, the process will get an extra drift in the direction given by b prime, by the atom of b prime. And it turns out that if you consider these kind of coefficients, what you get as a boundary trace is what is called the phase type Levy process. And it's well known that phase type Levy process can approximate any Levy process with completely monotone jumps. And here we see another manifest of that, because you can clearly approximate with purely atomic measures and piecewise constant functions any reasonable coefficients. Okay. So these are the nice pictures that I wanted to show you. But let me move to the Pde formulation. Okay, so that's essentially the same story as before, but now written completely in the language of PDEs. Again, people hating probably wake up. So we start with a generator of a shift invariant diffusion, which we call shift invariant elliptic operator. And that's just the operator that I wrote above. That's just the general second order elliptic operator. You may ask, what are the assumptions on A, B, C, D, and E, coefficients? Okay, I do not really want to write down these conditions because they get nasty. It's in some sense easy to work with arbitrary diffusion because you don't really need to specify the coefficients and the domains of generators and things like that. You just have a nice continuous process that you can characterize using well-known theorems. And when it comes to PDEs, you're doomed because if you consider two irregular A, B, C, D, or E, you can get a meaningless operator, and it's hard to nail down what are the precise assumptions. So instead of being formal here, let's be completely intuitive here. And on the other hand, if we want to write the generator of a regular shift invariant diffusion, we get something very precise. So we get very formal. We get the second order derivative, the second order elliptic operator without drift term, so just pure second derivatives. Coefficient y, the coefficient 1 at dyy, coefficient 2b at dxy, and a certain measure valued coefficient, a of dy, at the second order derivative with respect to x. And we need to assume that this is an elliptic operator, so a of dy should dominate b squared, so that this is really a positive definite form. But other than that, a can be any measure. It can have atoms and so on. And in fact, these are all the regularity restrictions here are needed in order to make the problem, the Dirichlet problem for that operator meaningful. So there are no really true restrictions on the coefficients here. And let me briefly mention the proposition, the informal result that I mentioned before when I was discussing the probabilistic picture, that every shift invariant operator L can be regularized, transformed into a regular operator in 3 steps. First, you need to change the scale. So you need to kind of put different levels at new positions. So transform y into a function of y. Then normalize it so that the coefficient at dyy is equal to 1. That doesn't really affect the Dirichlet problem because you just multiply your operator by constant, but you still require that operator to be equal to 0 applied to a given function. And the last step is what I call shearing. It's moving the horizontal lines slightly to the left or to the right, depending on y. So we replace x by a function x minus tau of y. Okay. And now in the regular case, the definition of the Dirichlet Neumann operator is pretty clear. It's just the first order derivative, the boundary derivative with respect to y. In order to get full picture, you should also allow for sticky boundary conditions in the probabilistic language, which means that you should allow to add a constant times second order derivative of f. That's just needed in order to get full generality, and it's kind of artificial in the Pde language, but it's perfectly natural in probability language. In the general case, the definition of the Dirichlet Neumann operator is a little bit counterintuitive, but what you need to do is just to unwind these transformations that are needed in order to regularize your operator. Okay, so instead of considering x minus tau of y, you need to come back to the original variable, so to add tau of y to the new variable x. Okay, that's undoing shearing. And then you need to take the derivative with respect to the variable y after change of scale. So you need to undo transformation of y into phi of y. So you consider phi inverse of y here. Okay. So that looks artificial, but it's in fact a very natural definition of the Dirichlet Neumann operator. Okay. And now, what is U? U is the solution of the Dirichlet problem. So we want that operator L applied to U to be 0. And you have prescribed boundary conditions, but it turns out it's not really easy to define the notion of a solution rigorously in that generality. So things get a little bit technical here. But in the end, once you do that, you get the theorem that is a perfect counterpart of the probabilistic theorem. For every shift invariant elliptic operator L, the Dirichlet Neumann operator is the generator of a Levy process with completely monotone jumps. Hence, a Levy operator with diffusion coefficient alpha, with drift beta, so the second order coefficient alpha, first order coefficient beta. There may be some killing term in probabilistic language, so we can have gamma times f as well, plus the non-local term. This is the usual non-local term in the Levy operator business. But the function mu, the kernel mu here, is very regular. This is precisely a function which is completely monotone on 0, infinity, and a mirror image of that on minus infinity 0. Okay, and once again, if you just consider regular shift invariant diffusions, regular shift invariant operators, there's a one-to-one correspondence between operators k of that form and the corresponding elliptic operators L. Okay. And now you can think that this is just a variant of the other theorem, and that was what I was thinking, but it turns out not to be really true, because there's a rule of thumb that the Dirichlet Neumann operator should generate the boundary trace process, but there's no general result like that in the literature. At least I was unable to find one. And it turns out that instead of proving such a general result, which turns out to be rather difficult, I was not able to overcome all the technical details, it's in fact easier to prove the two theorems sort of separately. So the key ingredient is, again, the analytical result of Eckhart and Kostienko that I mentioned before. But this time, the tools needed are completely different. And the two papers are, in fact, not really related one to another. They're sort of independent. They prove the same theorem in two different languages, but the proofs are essentially different in some sense. I was greatly surprised by that observation. So here the tools essentially is the Fourier transform. So once you write the Fourier transform of the problem, you easily see that this is reduced to solving a second order ODE. And this is not really the ODE considered in Eckhart and Kostienko, but an easy manipulation turns one into another. So that's not really, philosophically, it's a very simple proof. Just do the Fourier transform, write the ODE, solve it using the result of Eckhart and Kostienko, done. There's one more ingredient. You need to know that the spectral function given by Eckhart and Kostienko corresponds to the Fourier multiplier of the operator K of that form. And that was happily or luckily the part of my other project, which turned out to be very useful for that one as well. And that's it, essentially, except for all the technical difficulties that you need to overcome. So, for example, I already mentioned that it's difficult to define the notion of a solution in that degenerate case. And in order to do that, you need to work with weak or distributional derivatives, or in fact, something in between in some sense. And you need technical tools like absolute continuity of lines, characterization of weak differentiable of a function, and many other really nasty technical details that I don't like. So I really like the probabilistic paper. I really do not like the argument given here because it's very technical. And in the end, they both prove the same theorem in different languages that are not easy to translate one to another. And I think my time is up, so I'll stop here. I initially planned to mention a few words more about the proof of the analytical result, but since I am over time, I'll stop. Thank you very much for your attention.
Thank you very much, Mateusz. Wonderful talk. So let me open the mic for a question from the attendants. Okay. Yeah.
Hi. Go ahead, Juan Carlos.
Yes. So I wanted to ask you if this paper of Eckhart and Kostienko is in the dimensions that you are working on. I mean, in R plus times the positive.
No, the paper
line?
is really on the one-dimensional ODE. So what if you do that Fourier transform, what you end up is a second order ODE of the form phi double prime of y plus a of y phi prime of y plus b of y more or less equal to b of y phi. These are not the coefficients mentioned above. We need to do this carefully. B of y phi of y equal to lambda phi of y more or less. And there's there's also the Fourier variable psi somewhere here hidden. And yeah, we need to do the Fourier transformation to write it carefully. So I think there's I think psi over here, and there's not really lambda here, but psi square or something like that. So more or less, they just consider a second order ODE with a spectral parameter psi, and they study the dependence of solutions on psi. And in that language, what they really do study is the boundary derivative of phi, so the derivative of phi at 0, as a function of that spectral parameter psi. Okay, that ODE is wrong. in this to be fixed. But more or less, that's a problem they consider. In fact, they consider it it's formulated in a somewhat different language, and I had a hard time understanding what they wrote there, but it turns out to be really what is needed here. So the translation into that language is done in that analytical paper, and there's a whole section which tries to relate that result with what is needed here. But it was really lucky that I found that paper, because that's essentially the problem of sort of an inverse problem. So the characterization of spectral functions of certain second order ODE that goes back to the branch, and essentially that's a method that was used by Krein in the development of theory. But you can't just apply the result of Krein. You really need to go back and do all the hard job. That's a very deep result, which requires, I think, a lot of technical abilities and good recognition, good understanding of that theory, which certainly I do not have.
I have a question, Mateusz. So I understand this correspondence, no, between the extension and the non-local operators is very non-constructive, no? But
that's true, unfortunately.
And then in Caffarelli Silvestre, the big advantage, I would say, the reason they can treat these local problems is because, well, they knew something about the weights. No, there was this theory of Markenhaupt weights with Fabes, Kenis, Serapionica. They could extend all the regularity estimates. Is it somehow no? I mean, I don't. For sure, there are no representation formula for this coefficient for these weights. But can you say something about being Markenhaupt in terms of the Levy measure of something in that direction?
That's of course a very good question. Honestly, well, I don't think even in the symmetric case there's much relation is known between the say regularity of the coefficient, say when it belongs to the Markenhaupt class, whichever, and what is the corresponding boundary trace or Dirichlet to Neumann operator. So already there, I think it's too inexplicit to study these kind of properties. I remember that there's a result that kind of tells that if something is Lipschitz, then you can tell something about the Dirichlet to Neumann operator, but I don't think even vice versa. So even in that case, when you really want things to be very regular like Lipschitz, it's hard to translate one into another. And of course, the result of Eckert and Kostienko is just the existence and doesn't tell you anything about regularity. So in particular, if you want to study your process and you don't know what the corresponding coefficients are, or you want to study a certain non-local operator, and you cannot really figure out what the corresponding coefficients are, you can't really say much about the regularity, I suppose. And that's, of course, a very good question that I was a little bit thinking about, but I kind of stopped working on that at some point because I figured out that I can say essentially nothing about that. And that was about the symmetric case. In the non-symmetric case, I did not even try to study that problem. But any ideas are welcome here. I mean, that's of course that will of course allow using a lot of machinery of local PDEs to handle these kind of non-local operators. And unfortunately, I'm aware of no results in that direction.
Thank you. Victor, you have a question?
Yeah, sorry, I actually may have a lot of questions, but I will just ask a couple. Did you say something about why you cannot take any Markov process X? I mean, because I think you can do more or less the same things. You will, as you said, maybe you will not get a Levy process, but you will get a Markov additive process. So non-local operators maybe for the process Y subordinated by X subordinated by the inverse local time of Y. So for instance,
Yeah.
let's think about X being a level process on RD.
Okay, so yeah, there are many ways to formulate the problem. The one that turned out to be very fruitful here is when y is just so in that direction you just have the Brownian motion, and in that direction you have a y dependent process, which I really wanted to be a diffusion, because in that case we get a nice local characterization of non-local operators. But of course you can consider that one to be just a Markov additive process with a regulator term given by the Brownian motion. And indeed you will get something like well, I think even it should even be Levy. I mean, it's certainly translation invariant, so it should be a Levy process on the boundary as say a boundary trace, so the process of jumps on the boundary. And in principle, you should be able to do a similar description. So take a Fourier transform of that and write down, well, at least in the Pde language, what is the Fourier transform of u of psi y. And of course, so the second derivative of u of psi y should be something like, well, that the generator of that one, the Fourier symbol of the generator of that one, which should be some negative definite functions called psi, but it's again y dependent, so the psi of psi y times u hat of psi y. Yeah. And in our case, this is just a simple second order term, like a of y psi square plus b of y plus ib of y psi. Yeah. So this is the ODE that I should have written here, right? So ignore that one and take that one and for the left-hand side, I mean, with a minus sign here and equal to 0. So instead of equal to 0, just put the spectral parameter here. Yeah, so if you're able to solve that equation in the Fourier variable, you're good to go and you can identify the boundary trace. But I do not really expect there will be much. I mean, okay, you can calculate just what the boundary trace is, but I would not expect something like you can get boundary traces of that class for that kind of process of psi, because you just have too much freedom in choosing that psi of y. Yeah. There are just too many Markov additive processes if you allow for jumps in some sense. So it's not to say that this is not interesting. It's just that for this particular problem, like characterize all boundary traces and give a class where you have one-to-one correspondence, it looks like the local case is doable, and the general case, I wouldn't even know where to start in some sense. Yeah, there's just too much space.
Yeah. Okay, but actually, the other question is, when you're using excursion theory, I guess you're using that for determining the Levy system of the process, isn't it?
Yeah, essentially, yes.
Yeah, and then, okay. Yeah, that's what I was thinking, that maybe you could consider something more general, because it's not that this is general enough or interesting, it's not enough. It's just that when you go to the excursion theory point of view, there are many things that work in a very general setting. That is what I was thinking about that. So if that is the way to do it, then maybe there's
that should be possible. So if you start with some nice psi that you can handle, then you should. I mean, in terms of solution of that kind of differential equation, you should be able to describe the jumps of the boundary jumps of your two-dimensional diffusion. How explicit this can be, I have no idea really. But that's certainly a good point. Yeah. And of course, you can do the same in higher dimensions. There's nothing that restricts you to consider a d-dimensional process in the x variable. But then again, this is sort of a more general direction where you can think what kind of processes you can get. but the description of the boundary traces, at least in the local case, will not be as nice as in dimension 1, because you, on the other hand, here you have just too little space. You just have a matrix here and a vector here, and there are just too many jump type processes in some sense, even stable ones. You have a spectral measure which gives you infinitely many coefficients in some sense.
Yeah, that's very complicated, yeah. And also in X, you could also put a Levy process, not a diffusion, yeah. You will, so you will have more jumps and so, but
yeah, that's of course a good question. Yeah, I didn't really try to see what you can get, but certainly that's a natural question to ask. What happens in higher dimensions, and perhaps not necessarily in the local case, but when you allow for more processes in the X variable. So on one hand, you make more space to look for, and you also make more space for possible outcomes. So that's perhaps a hopeful problem.
okay. Thank you very much. It's very interesting. Thank you.